Good day, everybody. Today I want to look at convexity. That's a curve which is concave up, and how the derivative of the curve and its second derivative relate to whether the curve's convex or not. So first, let's look at the definition we're going to use. This is for a continuous function. It doesn't have to be differentiable here. So basically a curve is convex or concave up if every line segment joining the curve is always above the curve. So there's a couple of hand-drawn convex curves and a couple of hand-drawn line segments connecting the curve, and notice the curve is always below the line segment. Mathematically, what that means is f evaluated at any point in between x1 and x2, f evaluated at that point will always be below the y value connecting those endpoints. And so this is the way to get the y value of this line segment. So the y values go from f of x1 to f of x2. So this is our definition of convexity. F evaluated at any point in between x1 and x2 is below the line segment connecting the y values, f of x1 and f of x2. So that's true for every x1 and x2 in the interval, and for every t from 0 to 1 that connects the line segments. So let's look at a few curves. The first well-known curve, x squared, and you can see I can draw line segments connecting the curve, and it'll always be the case that the line segment's above the curve. What will also be true is the curve is always above any of its tangent lines. So if you graph any tangent line to the curve, then a convex curve will always be above it. This is, of course, assuming differentiability now of the curve. And then if the curve has a second derivative, we'll see that the second derivative will be non-negative, greater than or equal to 0. A few other convex curves. You got the exponential. Of course, its second derivative is always positive. So any secant line is always above the curve. Oops. And every tangent line for the curve always lies below the curve, or the curve is always above every tangent line. E to the negative x is concave up, convex as well. You can easily check by looking at its second derivative will always be positive for every value of x. And looking at its tangent lines, the curve is always above any of its tangent lines. So it's concave up, convex from negative infinity to infinity. A curve is concave down, or sometimes it's concave, but if it always lies above any of its secants. So here, I can't quite see that, but oops. So in this case, the curve will always lie below any of its tangent lines. Its second derivative will always be negative or 0. And another equivalent is the negative of the function is concave up or convex. So here's the negative of log x, and it is concave up or convex. Most curves that we look at in regular classes will either be concave up and concave down on certain intervals. For example, arctan, it's concave up from negative infinity to 0, and then concave down from 0 to infinity. Here's the 0 to infinity part where it's concave down. Another simple curve, x to the fourth minus 2x squared minus 2. This will have change of concavity at plus or minus the square root of 1/3. If I look, like it looks above, well, the curve looks to be below this line, but we have to be careful because it has to be for every line segment. And if I move this, then you can see, well, the curve isn't always below that secant line. So it's right around the square root of 1/3, which could be kind of near 0.6, is where that inflection point would be. Or looking at the tangent line, if we see the curve's always below the tangent line, so it's concave up, and then we reach this inflection point, and then now the tangent line's above the curve, and then we reach it again. You can also notice the rotation. The tangent line's kind of rotating counterclockwise, and then it switches to clockwise, and then back to counterclockwise again. So where that switching takes place is where the change of concavity or inflection point occurs. Again, this curve looks to be like it could be concave down, but it actually happens at 2 root 2, around 2.8 is where the change of concavity would be. If I go here, see, so you have to be a little careful. But it would be concave down up until 2 root 2, which you can almost see a little better with the tangent line. So there it is. So it switches from rotating clockwise to counterclockwise at that inflection point. So it goes. So sine x, lots of change of concavity. So let's look at the proofs. So the first thing I want to prove is that if the function's convex and differentiable, then the function's always above its tangent lines. And again, to be convex means it satisfies this inequality. F evaluated at any point in between two x values, the function will be below the line segment connecting. So this evaluates the y value of the line segment that corresponds to this. All right, so if f is convex and differentiable, the function itself, though, is below the tangent line for all x. So proof, given any x not in the interval where f is convex, and any x in the interval where f is convex, x not equal to x naught, then since the function's convex, we have this was our definition. I replaced x1 and x2 with x naught and x. So x1 and x2 got replaced with x naught and x. Now I'll distribute this f of x naught to 1 and t and move them to the left hand side. So then we get this line. Now I'm going to divide by t. So we have f of x is greater than or equal to this minus that, right there minus that, divided by t, and then also this divided by t, which will just be f of x naught. And you could use L'Hopital's rule. I'm going to take the limit as t goes to 0, but I decided to do it a different way to get f prime in here. I multiplied and divided by x minus x naught. So do that. So obviously this is the same as that. Just multiply and divide by x minus x naught. But now I'm going to call t times x minus x naught, and this is not 0, but I'm going to call that h. And h could be negative, it doesn't matter. But so if that's h, then I have f of x naught plus h minus f of x naught divided by h times x minus x naught plus f of x naught. And that's true for all h not equal to 0 and in this interval, kind of a punctured interval. And so we can take the limit as h goes to 0. And if you do that, then this just becomes the derivative. And that shows what we wanted to prove. But this is a if and only if. So conversely, if f is differentiable and it's always above the tangent line, then f will show f is convex. Okay. So if f is differentiable and it's always above every tangent line in an interval, then f is convex on that interval. And proof given x1, x2 in the interval. For each t, I can set this point in between them. I'll just call it z for now. And you can write z in different ways if you distribute. So that z is in the interval from x1 to x2, assuming x2 is bigger, and then that's in I. It works if x1 is bigger than x2, either way. Anyway, so by hypothesis, since this is true for all x, x naught, I'll put x2 in for x and z in for x naught in this assumption. Right, so we always have the function is above a tangent line. So f of x2 must be greater than or equal to f prime at z times x2 minus z plus f of z. Just replacing x naught with z, x with x2. And similarly, you can replace x with x1 and x naught with z. So we get this line. I'll multiply this top line by t, where t is in the interval from 0 to 1. So t is positive, so it won't change the inequality. And I'll multiply this bottom equation by 1 minus t. So again, that's positive, won't change the inequality. And now I can add these up. So I get this is greater than or equal to the sum of these terms. So I've got this term, just rewrote it here. I've got that term, rewrote it there. I've got this, I decided to distribute. So I've got f prime of z times x1 minus z times 1, and then also times minus t. So those are those two. And then we have f of z times 1 and f of z times negative t. Okay, we ran out of room, put down here. You can see these two cancel right away. I've got f prime of z times t times x2 minus z. And then I also have it here, t f prime of z times x1 minus z, but this is minus. So I distributed this minus and made it negative x1 plus z. So that takes care of this and that. And then I've got this f prime of z times x1 minus z. And I'll just put back what z equaled. So z was x1 plus t times x2 minus x1. Right, if we look back, if you want to see it real quick, z. And then lastly, plus f of z. So that's the last term. So here the z's cancel. So we just get this plus f prime of z. And now here the x1s will cancel. And we'll just get t times x2 minus x1, but with a minus. So keep right here. And then plus f of z. And now these two terms are identical, except one's being subtracted, right? You can pull this minus t out front. So they cancel, and you just get f of z. But what did f of z equal one more time? It's this quantity right here. So that is less than or equal to this. And that was true for any x1 and x2. x1 and x2 arbitrary. So f is convex. So that completes the if and only if. So if f is convex and differentiable, it's above every tangent line, and conversely, if f is above every tangent line, it's convex. Sometimes we take as the definition that the second derivative is positive, and well, if the second derivative exists, that will be true, or at least not negative. So let's look at the proof of that. So if f is convex, this is my definition. Again, I don't even need to be differentiable for this definition. So first I'll look at if the derivative exists and is greater than or equal to 0, then f will be convex. So for the proof, pick any x1, x2 in the interval, and t in 0, 1. And without loss of generality, we'll log, let's assume x2 is greater than x1, and we could rework it if x1's less than x2, but what I do below, I'm going to kind of need x2 bigger than x1, and then you'd have to redo some things if x1 were bigger than x2. But we'll set c, I probably should have used z again, but I use c, so c equal to that, this point in between x1 and x2. Then this quantity, and f of c is going to be f of that point in between. I want to be greater than or equal to 0, so that's what I want to show. But right now I'm just going to follow a string of equalities. So with this quantity equals these two terms I just rewrote, and then minus f of c I rewrote as 1 minus t plus t. So that's the same thing because that equals 1. But now I'll take the 1 minus t f of c part and combine it with the 1 minus t f of x1, and then the minus t f of c and combine it with this t f of x2. So I split that f of c into the two parts there. And now c is in between x1 and x2, and x2 is bigger. So let's change the order here. Since c is bigger than x1, f of c might be smaller than f of x1, but c is bigger than x1. So I'll switch this order. It cost me a minus sign out front there. That was the only change there. And now I'm going to use the mean value theorem. And in case we want a refresher on the mean value theorem, if f is continuous on an interval AB, differentiable on the open interval, for us it'll be differentiable everywhere, but then there is a c, there is some point in the interval so that f prime at that point is f of b minus f of a all over b minus a. Again, this c is different than the c I'm using in the other proof. I probably should have used z a second time, but anyway. So if f is differentiable, then somewhere the derivative will equal the slope of the secant line. And the way we're going to use it is, well, if you multiply by b minus a, you could say f of b minus f of a is f prime of c times b minus a for some c in that interval. There has to be some value where that's true. So I'm going to replace this f of c minus f of x1 with f prime at some point in between x1 and c, c in this interval. So f prime, so f of c minus f of x1 will equal f prime at c times c minus x1. And similarly, f of x2 minus f of c will be f prime at some point in that interval from c to x2 times x2 minus c. So I use the mean value theorem to replace each of these with that. And now I'll put in what c equals. So c, we have it right here. So c minus x1 will just be x2 minus x1 times t. So that. And x2 minus c is x2 minus, and I'll use this version, minus that, and minus this. And here I've got this x2, you can factor it out. You got a 1 minus t, and then we've got this 1 minus t here, times x1. So I can factor the 1 minus t out, and I do that, except now these will all be positive, so I put it first. So I've got t, 1 minus t, f prime of eta, times x2 minus x1, that's this, and then minus t, 1 minus t, f prime of c, times x2 minus x1. And now these are almost identical. I can factor out the t, 1 minus t, x2 minus x1, and I just have f prime of eta minus f prime of c. And I can use the mean value theorem again, but on f prime, not f. So if you use the mean value theorem on f prime, this will be f double prime at some point in between c and eta, use gamma, times eta minus c. And now, because I was assuming x2 is greater than x1, everything here is positive. F double prime we only assumed was greater than or equal to 0. So, but this is positive, that's greater than or equal to 0, that's positive, that's positive, that's positive. So everything's greater than or equal to 0, so the product's greater than or equal to 0. And that's what I wanted to prove. If you follow this first line, everything was equal to, and then I got greater than or equal to 0. And so if that's greater than or equal to 0, I can move this f of c over and then just rewrite what f of c was. F of c was f of 1 minus t x1 plus t x2. So that's less than or equal to. And that's the definition of being convex. So if the second derivative is always positive, the function is convex. And it's a if and only if, so we will show conversely, if f is convex and the second derivative exists, then the second derivative is always non-negative. So for the proof, if f is convex, then we know this is true for all x1, x2, and I, and all t and 0, 1. So given any x in the interval, let's set d to be the distance that x is to the endpoint of the interval, or 1, whichever is smaller. Just in case we have an infinite interval, we don't want d to be infinite. So it's the smaller of either 1, it's small enough, or if we're really close to an endpoint, then how close we are to the endpoint. So whichever is smaller, the distance x is to the endpoint, or 1. And I'm looking at an open interval, so x can't be an endpoint, which means d is always definitely positive and not 0. Then for any h not equal to 0 and smaller than d, we can set x1 to be x minus h, x2 to be x plus h. And actually h could be negative, but it won't matter. I'll also set t to be 1/2. So it's true for all t in 0, 1. So in particular 1/2 works. So if t is 1/2, then we have 1/2 f of x1, which will be x minus h, plus t, which is 1/2 f of x2, which will be x plus h, minus f of 1 minus t, which is again 1/2 times x1, which is x minus h, plus t, which is 1/2 times x plus h, and that's greater than or equal to 0, since our function's convex. Well, let's multiply through by 2. That'll keep the inequality. So if I multiply through by 2, I get this. Notice what's inside the parentheses is just 1/2 x plus 1/2 x, which equals x. And there's also a minus 1/2 h plus 1/2 h, and they cancel. So multiplying this by 2 gives me this. So I can now also divide by h squared. And we're looking at h in this interval. H could be negative again, but h squared will be positive, and it won't be 0. So if I divide by h squared, then this is greater than or equal to 0 for all h in that interval. And if the second derivative exists, then f double prime is the limit as h goes to 0 of this difference quotient. This is a way to get the second derivative through a limit of a difference quotient. We can verify that with L'Hopital's rule. I actually did do that. So if f double prime exists, and I'm looking at this difference quotient, and I want the limit as h goes to 0, well, notice you would get 0 over 0 if you just plug in 0. You get 0 on the bottom, and then you get f of x plus f of x minus 2f of x, you get 0 over 0. So we can use L'Hopital's rule. So the limit as h goes to 0, so we're doing an h derivative. So this will be f prime at x plus h. This will be 0 when you do an h derivative. And this will be f prime at x minus h times the derivative of what's inside, which will be negative 1. And again, we're going to get 0 over 0 if you just plug in h equals 0. You get f prime of x minus f prime of x all over 0. So 0 over 0. So we can use L'Hopital's rule a second time, and then we'll get f double prime x plus h, again it's the h derivative here, f double prime x minus h times another negative 1, so I get negative 1 squared, and then divided by 2. So now I have this limit, and now we can plug in 0 for h, and we just get f double prime of x plus f double prime of x all over 2, or f double prime of x. So that verifies this difference quotient will give us the second derivative. And that completes this proof that if f is convex and the second derivative exists, the second derivative must be greater than or equal to 0. So there we have it, our look at convexity being concave up. If the second derivative is positive, we're concave up. If the curve is always above its tangent line, it's concave up. And the definition being every secant line is always above the curve. So hope you found that useful, and just remember to keep on thinking about math. Enjoy the rest of your day. Thank you. Goodbye.